Welcome back, chemistry fans. What we are going to try and attempt is to give you the solutions to this equilibrium quiz. Let's jump into it right now. I've got a few marks on it. Let me erase those so that we can work through this multiple choice. Okay, so it says all of the following are going to force more products to be made. That's what it's stating here. Whether or not you can understand that that's where we're headed here, they're saying all three of these are going to make it go towards the product. There's only one of them is going to make it go backwards. So let's take a look at these individually. On A, decrease the pressure. Well, that means that you're actually going to increase the volume. If you are decreasing the pressure, you are letting go of the force on top of the gases. So it's increasing the volume. If I get rid of the solids, that means that there is one material on the left, 2 moles of gases on the right. By increasing the volume, I need to shift towards that 2 molecules to fill up that space. So that's what we're going to do. Hang tight. Okay. So now, if we remove gaseous product, that means also that product is over here. So if we remove anything from this side of the equation, the reaction is going to shift to go and fill it up. It's the you have a divot, I need to go and fill it up situation at the beach. So that is not going to be a correct answer. Decreasing the volume, that means that you're making it smaller. That means that if the volume goes down, we need to go towards the side where there are fewer particles. This is your correct answer. Increasing the temperature means that you are putting pressure on the left side. It needs to shift to the right. That means it is also not a correct answer. So let's then move to number 2. Le Chatelier's principle, a second question about it. Okay. So the partial pressure of CO, what this is talking about is the amount of this material. If you have more partial pressure, you have more material. So by using the term partial pressure, we're not talking about anything other than just making more of the CO, which is again on the product side. And it says equilibrium can be maximized. In other words, how do I make more of the products? Okay, so how do I do that? If I have a high temperature, now what this means over here, it is producing heat. So it's on the product side as well. So if I increase the temperature, equilibrium is going to try and shift it to the other side. That's not maximizing what I want, which is the other material. Okay. So number 2, same story, high temperature is going to shift it. So we don't want high temperatures. That's not going to produce more of the product. So it's gonna be one of these other ones. So if we have low temperature, that means the reaction is going to try and reverse to give it more of these products. So both of these are viable answers. Now, which one causes it to have to go towards the right side? Well, there are 2 molecules on the left, there are 3 molecules on the right. So we actually need it to do low pressure so that it will have high volume. And that's what we want. So our answer should be low temperature and low pressure. All right. Let me go on to question number 3. Question number 3 says, if the reaction has an equilibrium constant greater than 1, which of the following statements is correct? Well, what that means, if it's greater than 1, it means there's more products than there are reactants. So the reaction is product favored, is what's happening here. Okay, number 4. It says, okay, well, let's write an equilibrium constant for this. You can cancel out the solid. We have no products, or we have no reactants in this. So the KEQ, the KC, is going to be equal to products over reactants. Well, we got no reactants because that's being canceled out. So what we're left with are the 2 reactants right there. That's all that we have. Okay, so question number Here is where we get into the most challenging question. This is dealing with the ice chart. So we'll start and build one of the ice charts. So I've got my reactants, which are H2. You know what? I'm just going to use what's written here. It's just as fine. So I'm going to just use this. And I'll list out my ice. Okay, now I am starting with one of the H. I am starting with, with the H and 2.5 of the I2. I don't have any HI, so it means I got to list that as 0. Now the change amount here, so this is going to lose an X, this is going to lose an X, but this is going to gain 2X in the process. Now, because we want to make the math simpler, what we get to do is we get to ignore those X changes for the reactant starting material. So now I have my equilibrium, but I still don't know what the X value is. So I need to actually calculate that. So I'm going to set this up as KEQ, which is KC in this case of 129. Products over reactants. My product in this case is 2X, but because it is 2 as the coefficient, it needs to be squared. Underneath the reactants, 1 and 2.5, simplified. So I am going to now multiply 129. I'm going to put this on a good calculator and not on my phone. You should do the same. 129 times 2.5, and you get 322.5 is equal to 4x squared, because 2x times 2x is equal to 4x squared. All right, so we're going to divide both sides by 4, cancel out, and what you get is 80.625 is equal to x squared. So we're going to do the square root of both sides, and you get 8.9. You could round that to 9 as your answer for x. Now, what do we do with that? I only need this value right here. That's the only value I need. So I'm not worried about anything else. All I'm going to do is do 2 times that value. So my final answer for this is going to be 17.95. If you want to round that up to 18, that is perfectly fine. Units on that one are molarity. All right. So this is everything that I wish to share with you. Thank you very much. I will talk with you again soon. Farewell and goodbye.